Okay, and so our next speaker is Grigg from
Curtin University.
Curtin, that's it. I was trying to find out where it was on there.
She's good.
Who's going to tell us about space situational awareness for SCAR-Low. So thank you.
Thanks.
I'll give you a 2-minute warning.
Cool. Hi everyone, thanks for giving me the opportunity to speak here today. My name's Grigg. I'm a PhD student at the International Centre of Radio Astronomy Research, which is based at Curtin University in Western Australia. I'm also an employee of Doug Technology, a local supercomputing company, and I've been using some of their software as part of this work as well. So the title of my talk is Space Situational Awareness at the Site of the SKA-LO using SKA-LO prototype radio telescopes. So the SKA-LO, as most of you probably know, is half of the square kilometre array. This half is being built in Western Australia, with the SKA-Mid being built in South Africa. Cool. So this is the site where the SKA-LO is being built. The traditional name is Inyarimana Ilgadi Bundara, which in the Wajiri Yamaji language means sharing the sky and the stars, and it's also known as the CSIRO Murchison Radio Observatory. So in this picture on the right, you can see a few of the radio telescopes which are currently at the site. The one on the left is the Murchison Wide Field Array, which is the largest telescope on site, and you can also see 4 other circles in the background, if this works. And I'm interested in 2 of those radio telescopes. And so those are the Engineering Development Array 2 and the Aperture Array Verification System 2. So we call these the EDA2 and the IAUS 2. These 2 radio telescopes are very similar. They've both got 256 antennas over a 30-metre diameter. The difference between them is the type of antenna. So on the left, the EDA2 uses a dipole like the Murchison Wide Field Array, and on the right, the IAUS2 uses an antenna, scalar antenna, which is more like what will be used for the SKA-LO. So I've been using these 2 for the work that I'll present to you today. So some early work back in 2013 done by the Murchison Wide Field Array found in some early commissioning data sets that there were objects which move very quickly over the sky, which were found out later to be aircraft and satellites. And an early paper predicted that we should be able to detect satellites with a 0.5 metre radius out to a distance of 1,000 kilometres. And then a follow-up study a couple of years later started to look at the interference due to some of these satellites and radio frequency interference in general. And on the right in the figure there, you can see the RFI levels at the Murchison Radio Observatory compared to the LOFAR telescope in the Netherlands. So how do we detect satellites that are passing over? So we use 2 methods with our radio telescopes. The first is just detecting direct transmissions from the satellites. So a satellite passes over, it transmits down towards Earth, and if our radio telescope is underneath at the time, we can pick up this signal, and then we can position this on the sky from where it came from. The other method that we use is called passive bistatic radar. Passive, meaning that we don't have to put out any signal to detect the satellites, like some radar systems. And bistatic, meaning that the source, which are FM transmitters, and the receiver, which is our radio telescope, are spatially separated. So there's FM radio transmitters all over Australia, some very high powered, up to 100 kilowatts. And these provide radio for cars and houses. So they actually also act as an illuminator for satellites passing over. So if the radar cross-section of a satellite is large enough, or the area which can reflect the radiation as it passes over, the FM radio, which is mostly directed over the land, some of it goes up into space, reflects off the satellite, and then we can detect this with the radio telescope. So part of the work that I've been doing so far is surveying different frequencies over the SKA-LO functional bandwidth, which will be about 50 to 250 megahertz. 350 megahertz, and I've handpicked some frequencies which were interesting so far. So some which are protected under the International Telecommunication Union's radio regulations, some which overlapped FM radio, others which were known satellite downlink transmission frequencies, and others like digital television band and any other ones that I thought were interesting. So if you haven't seen radio data before, this is what it looks like. These are the images that we produce out of the radio telescopes, and this is a combination of all of the energy which is incident to each of the antennas in the radio telescope, and we combine these into all sky images. So on the left here, this is actually an image of the full sky. You can see the rough outline here, horizon to horizon. And in the centre, at 98.4 megahertz, the sun's very bright, and you can see the Milky Way to the right over here. And there's these other two sources of radio frequency interference over the sides. The one on the bottom right is due to a phenomenon called tropospheric ducting. So there's a transmitter 300 kilometres away from the telescope. And even though it doesn't have line of sight to the telescope, this energy goes up into the troposphere, refracts, and then comes back down, and we can detect this often very strongly with the radio telescope, and we often have to throw out data due to this as well. So what we do, we observe for sometimes a few days at a time, and we produce sets of images which contain anywhere between 2 and 10 seconds worth of data. So the ones here contain an 8-second snapshot of the sky, and then we difference them. So adjacent images we subtract, and that means that we can see what's changing in the sky over that time period. And we call this difference imaging, and this is the image that you can see on the right. So very bright sources like the sun do actually move over the sky over the course of 8 seconds. So you can see like differences due to that. But you can also very clearly see sources of interference like change in the signal at this transmitter. And that's what we want to see when satellites are passing over. So in a paper that we published last year, we introduced a technique which is quite simple. It's called shift stacking. So on the left, there are images of the International Space Station passing over, which is this blob here. And what we do is take the predicted position of satellites from, we can just take from an online database, and we shift the position of the satellite in each frame to the centre, which is in the red box here. And we also rotate it. And then once we've rotated them all, we can then stack them all together or average them together. So you can see on the left all of the images that we've stacked together, and then on the right is the stack that we get, and this nicely increases the signal-to-noise ratio across the path of the satellite. The next one is a nice example of this working, of the Hubble Space Telescope. So on the left, it's quite difficult to see any signal in the middle of the red box, but you can see when we stack all of these images together that there's some nice signal on the right in the stack. And that shape that you can see with the white below the black inside the red square, the white signal is the signal in the current frame, and then the black is the subtracted signal from the previous frame, and the separation between the two is how far it's travelled in that time. We also use another technique called frequency differencing, which also increases the signal-to-noise ratio nicely. So rather than differencing in time, we do it in frequency. So we obtain 2 frequency channels simultaneously, one where we know the radiation is going to be present in, and the other where we know it's not. And then when we difference them, there's no movement in time of anything. It's in the same time step, which is why there's only one white shape in the one on the right. And yes, we get about a double signal-to-noise ratio because of this. You can also see in this one as well, which is quite nice. Sorry, the laser stopped working. To the left of that image, you can also see the illuminator, the FM transmitter, which is the reason that we can see the International Space Station passing over in this frame. So I just wanted to show a few examples of things that I found through doing this survey as well. This is just a couple of isolated examples. I found a lot of interesting stuff. This is an example of the International Space Station passing over, 2 different passes in FM band, which is 96.5 megahertz. So you can see the contribution in the bottom right of both of the images from the local FM transmitter, but you can quite nicely in the 2 of them see the International Space Station passing over as well. All of the flashes in the images are from meteors, so as the meteors pass through the atmosphere, they ionise the air, causing a plasma which reflects radio energy quite nicely, so that's why we can see a lot of those. This example is a satellite called SOLRAD-7B, one which was quite interesting. So it's a satellite which was launched in the 60s and decommissioned pretty soon after, but we can still detect it. And it turns out that we can only detect it when sunlight's incident on the solar panels, so it's a zombie satellite. And you can see as it passes across the sky, it pulses. And in the 2 polarizations that we get out of the radio telescope, you can see in the graph on the right how these are out of phase with each other, and it's because the satellite's spinning, so it's a bit like a lighthouse effect. And as we record a few passes of this object, we can start to characterise the spin of the object. We've also detected Starlink satellites. So this is a paper that we published, which came out last week. At 159.4 megahertz, we didn't expect to detect any Starlink satellites. So this train that you can see passing over is still boosting into its operational orbit. And so we were able to have a conversation with SpaceX, and the engineers told us that this radiation is likely due to the propulsion or the avionics system, and that it's also likely broadband, sadly. So we call this UEMR, which is unintentional electromagnetic radiation. In the same paper on the right, we also showed detections of Starlink satellites at their designated downlink frequency. So this is completely legal at 137.5 megahertz. So they pulse once every 60 seconds. And these pulses are very bright, often well over 1 million Janskis per beam. And yeah, there's no chance of doing any radio astronomy in a frequency band like this. On the left is a new data set that we've acquired at 160.4 megahertz, where we can detect Starlink satellites passing over. These aren't still raising to their operational altitude, so we need to do some more investigation to see why we detect them at this frequency. Here's another satellite which pops up in pretty much every data set that we get. Doesn't matter what frequency it is across the whole SK low observing frequency. BGUSat, we've found a lot of these types of satellites that just transmit a broadband signal, and these are some examples at 185 megahertz. And they're amateur cube satellites, and it's probably due to cheap electronics that they emit these broadband signals, which unfortunately can be detrimental to radio astronomy research. We also detect plenty of aircraft as well in the FM frequencies. They're a lot closer to the telescope than satellites. They're 10 kilometres away rather than 400, 500 kilometres like in low Earth orbit. And in the paper that we published last year, we created that figure on the right, which was all the detections of planes in our data set. And I've got a video here as well. Hopefully we'll be able to see that. So I've been using it's actually geophysical interpretation software to visualise some of the data that I have. So here in 3D, I'm visualising just some normal images of the sky. And I switched to the difference images. So the blue path there is the predicted trajectory of the International Space Station. And you can see that lines up pretty nicely with where you can see the International Space Station in the data. And something I do with this tool is to render it in like a pseudo 3D, where you have the image as 2 dimensions and then time as the third. And then I make all the black amplitudes transparent, and then you can really nicely see all the radio frequency interference across like a whole data set. And I use this for quality control of data sets, assessing how much RFI is in the data, and also to make detections as well. And cool, that's good, thanks. And just to finish up, so far I've just been looking at frequencies which we've chosen, which we thought might be interesting. In the future, we'll do a more planned survey across the whole SKA low frequency bandwidth. And from all the detections that we've made so far, and all the ones we make in the future, we'll put them into a machine learning network to hopefully help make detections, like I've shown in the right here. So we can usually detect reflections off satellites out to about 1,000 kilometres, and we can detect transmissions all the way out to geostationary at 36,000 kilometres. So in the future work that we do, hopefully, we'll be able to characterise some of these signals to allow radio astronomers to know if their data sets are going to have, how much interference there's going to be from satellites at different frequencies. Thank you.
Thank you very much. Unfortunately, we don't have time for questions, as we need to get the next speaker.
Cool. Thank you.
So, thank you.